In this video, we introduce a rope-driven legged robot that uses reinforcement learning to climb steep, irregular slopes. We integrated an ascender module that climbs by winding ropes with a legged robot that adapts to uneven terrain using its 4 legs. To minimize the impact of rope stretching, the sheave is connected to a differential gear mechanism. A load cell mounted at the front of the module measures the force exerted by the rope, allowing us to estimate the tension in real time. However, controlling this hybrid system is challenging. Unpredictable tension fluctuations from uneven terrain are amplified by the robot's constrained motion, turning small disturbances into major risks and demanding a robust recovery strategy. To overcome this, we developed a reinforcement learning controller for the legs that focuses on stability and enables adaptive body height regulation. Our framework uses an estimator network to understand its situation from sensor history. Crucially, this estimator explicitly predicts the tumble stability margin, TSM. The TSM is a momentum-based measure that quantifies exactly how close the robot is to tumbling, even on complex 3D terrain. By learning to estimate and use this TSM as a reward, the policy gains an intrinsic, real-time understanding of its own balance. But resisting disturbances is not enough. Robot also needed a way to actively recover from danger. When the robot is in a hazardous situation, like a foot slipping, its TSM value becomes erratic, and its volatility sharply increases. We use this TSM volatility as a direct trigger for an adaptive height regulator. When instability is detected, the robot automatically lowers its body. This action lowers the center of mass, allows the legs to quickly re-establish stable contact, and reduces tumbling moments, enabling a rapid and robust recovery. We validated this framework on steep, rough slopes. On a 65-degree rough slope, the policy trained without TSM showed significant base vibration and frequent, inconsistent foot contact. Our full, TSM-aware policy was far more stable, demonstrating its effectiveness as a core component for balance. To prove the value of the height regulator, we created 2 hazardous scenarios. First, on an exterior wall with a slippery patch, the fixed height policy failed to cope with the continuous slipping, leading to severe instability or failure. In contrast, our adaptive policy instantly detected the high TSM volatility, lowered its body to regain grip, and then gradually restored its height only after the volatility subsided. This shows TSM is an effective early warning signal for recovery. Second, we made a catastrophic rope loss, causing the robot to swing. The fixed height policy, with its high center of mass, struggled to control the large swing momentum and failed to find a stable foothold. Our policy, however, immediately detected the instability as the swing began, lowered its body, and quickly secured contact. This action reduced the destabilizing moments and allowed it to recover. This proves that our TSM-based framework can blindly, without any vision, improve climbing safety even in extreme situations. Our robot can now stably ascend and descend across various angles, surfaces, and speeds. This stability-aware framework is a key step toward enabling robust and efficient legged locomotion in the world's most extreme environments.